is going to equals to this for your product minus delta G naught formation of your reactant. Okay, and this is a very important concept. Okay, so for most of the time when you do your exams, okay, you always see the equations. Okay, and then from equations you always want to know what your K is. Okay, and most of the time, especially in this class, this is how you get your K. Okay, that means you need to know your delta G naught. Okay, if the question did not provide the delta G naught information for you, then try to find out, can you calculate your G naught by yourself using this? Clear? Alright, so assuming today you have these equations in your final exam, I did not give you the delta G naught, but I give you a table that tell you about this delta GF of this guy, delta GF of that guy, delta GF of this guy, and this guy. Can you calculate this yourself? I hope the answer will be yes. Okay? And this is very important. This is very important. Okay? Alright, so in this example it's easy, right? Because you already tell you this. So then you can calculate your K very easily. So K is going to become equals to exponential negative delta G naught over RT. Okay? So this is going to equals to exponential negative 27.087 divide your R is 8.314 times T temperature, okay, 105 degrees C, which is 298 K. Okay, 298. So if you do the calculation, you found your equilibrium constant is going to equals to 1.8 times 10 to the negative 5. Okay, so this is your equilibrium constant K. Okay? So once you know this, okay, then let's say this is your initial condition, okay, and this is at equilibrium, and this is the change. So you must learn this already, right? Because in the Gen Chem 2, you learned the ice table, right? Initial changes at equilibrium. Okay, so this is initial condition. Then you know this thing is going to dissociate, right? So it's minus x plus x plus x, right? And then at equilibrium, you're going to have 0.1 minus x, and this will be x and x. Okay, so now you know your K is going to equals to x squared over 0.1 minus x. Alright? So this is how you do it when you are a freshman. Okay, so what's the difference between our class and the Gen Chem 2? Is instead of using the concentration alone, now you need to put in the activity coefficient. Okay, so what you have to do here is actually, the concept is all the same, but here you need to do this. Okay? Gamma squared x squared. Alright. Okay, so here I want to talk a little bit more about the equilibrium constant K. Okay, so we say if you do everything right, the equilibrium constant for this specific equation will be equals to A NH4 plus times A OH minus divided by A over NH3, right? Times the A of H2O. So this is actually the definition of equilibrium constant for the P-Chem. Alright? And then you also know activity of your pure water equals to just 1, right? So this is equals to 1. And you can write your A as gamma. I just use plus minus now, okay? Gamma plus times your M plus times your gamma minus M minus. And at the bottom will be gamma NH3 times your M NH3. All right? So gamma times gamma, it becomes gamma squared, right? And we did not write gamma plus or gamma minus, we write gamma minus plus squared. Okay, and then you multiply M plus times M minus. In this case, your M plus and M minus will be the same, right? So you can say, you can further simplify this equation as make M plus minus square. Alright? And at the bottom you have the gamma NH3 times M NH3. Okay? Typically, okay, for this weak electrolyte, okay, the convention for the activity coefficient for weak electrolyte, we make it equals to 1. Okay? So you know the final equilibrium constant K is going to equal to gamma plus minus square times M plus minus square divided by M NH3. That's all. Okay, so if you want to write the correct equilibrium constant expressed in terms of concentration and activity coefficient, this is the final form. Okay? So with this in mind, and then you go back to here. Okay, you will realize your K is going to equals to your gamma plus minus square, right? X is actually your M plus minus square. Alright? At the bottom is 0.1 minus X. Okay? Be careful. Here is minus X, not minus gamma X. Okay? Because the gamma is actually in the front, right? We said the gamma is actually in the front. This one is just the concentration term. And the gamma for your NH3 is equals to 1. So here, you should put X rather than gamma X when you do your calculation. Get it? Okay, so at the bottom, if you look at this equation, okay, you can also express in terms of activity coefficient and the concentration, right? And then we say the activity coefficient for the weak electrolyte is equals to 1. So this M inside, there's no gamma terms. Okay, because gamma is 1 here. Okay, and when you write here, okay, it's actually 1 times 0.1 minus X. So there's no gamma X inside because the gamma is actually outside here. Okay, so don't write 1 minus gamma X at the bottom. If you write it, then the calculation will be not accurate. Alright? Okay, so now you know this. Okay, and this is going to equal to 1.8 times 10 to the negative 5. Okay, so you have this equation. You have two variables, right? You have variable of gamma plus minus, you have a variable of the concentration term. But you only have one equation, then what do? Which one? So this is actually a tricky part when you do this calculation, okay? For a weak electrolyte, when you want to figure out the concentration of the Ki ion or the N ion, okay? You're going to have this problem over again and again. So this will always appear. So how do you actually solve this one? The first thing you do is actually you assume your gamma plus minus equals to 1. Okay? Once you have this, you can solve for your x, right? So you're going to know what is the concentration of this, concentration of lead. Okay? And once you have that, remember we have this Debye-Hughes limiting law. Debye-Hughes limiting law. Where we say the natural log of gamma plus minus is going to equals to negative 1.171 times your z plus z minus times your square root of I, 1 plus square root of I. Okay? So the I is determined by the concentration of your Ki ions. Okay, so once you know the concentration, can you estimate what is the gamma plus minus? So I is related to your concentration of your electrolyte, of your Ki ions, okay? Okay, so when you calculate this, if assuming this one, you're going to get your M plus minus, right? Once you have M plus minus, use these equations, you can estimate your gamma plus minus, right? So you're going to get a new gamma plus minus. Then what you do is actually then use the gamma plus minus to re-estimate your M plus minus. Okay? Typically, after you repeat this procedure for two times, you will get a consistent answer for your M plus minus and your gamma plus minus. Okay? And you can solve both of them. So that means you are going to know your M plus minus or the concentration of NH4 plus, concentration of OH minus. Okay? At the same time, you also know your gamma plus minus. Okay? So that's the things we are going to do now. Okay? Alright, so step number 1, we are going to say assume gamma plus minus is equals to 1. Okay? Then we solve this. And you are going to get the answer that your x is going to equals to 0.00133 m naught. Okay? So once you have this x, okay, the x is basically equal to your m plus minus, right? We also know the ionic strength, okay, for this V plus equals to 1, V minus equals to 1, Z plus equals to 1, Z minus equals to 1 case. I will just equals to your M naught. Okay, so this is actually the things we have learned in the previous lecture. Okay, so once you have this, then you can say, okay, the natural log gamma plus minus is going to equals to negative 1.171 times Z plus is 1, Z minus is negative 1. You take the absolute values, okay, times square root of 0.00133 divided by 1 plus square root of 0.00133. Okay? So when you do this, then you can actually calculate your gamma plus minus is going to equals to 0.960. Alright, so now you get a new gamma plus minus, right? So what you do is actually you use this number, put it back to here. So you're going to get, okay, so this is the second step, okay, you're going to get an equation of 0.960 squared times your x squared divided by 1 minus x is going to equals to 1.8 times 10 to the negative 5. Alright? Then if you solve for x, then x is going to equals to 0.00140 and not. Okay? So if you compare this, to this, because you have introduced different gamma plus minus, you get different x. Alright? Then what do? You use this one. Okay, say now you need to adjust. Okay, I is equals to 0.00140. And now, then you recalculate your gamma plus minus using this equation. Okay, so what's going to change is actually inside this square root is you need to put 0.00140. Okay, and then if you do that calculation, you are going to get a gamma plus minus equals to 0.959. Okay, and this number compared to that number, they are pretty much the same, right? So if you see the error is less than 1%, stop it. That's very close. Okay, so if you compare this and this, if the differences is less than 1%, then you're done. Okay? But if it is not below 1%, repeat this again. Okay? I guarantee this will appear in your final. So you get a new gamma plus minus, put it back to here, resolve with your x. Okay? Get it concentration, then get the ionic stress, recalculate your gamma plus minus. Okay? So you want to make sure you repeat this enough times so that the gamma plus minus and the concentration n plus minus reach a constant. Alright? Okay, so this is important. It will definitely appear in your final. Alright, this is pretty much all the knowledge you need to know for the calculations for weak electrolyte aqueous solution. Okay, now we need to talk about the strong electrolyte case. And you can go to your page number 12.